Do what?
Okay.
I would do that if we got work study.
So, good morning, everyone.
Time hours. How much do you want an hour?
Fun demonstration
Hour,
today.
the whole
My
one
favorite
hour.
sets. But before we get to that, just one announcement.
You get like 15 minutes.
I'm going to be described just a couple of weeks back, but looking for paid volunteers for the second of our entrance exams for the Science Honors program. Okay, so I'm not going to say much about it because most of you heard this already, but it's on April 27th, starting at 9 in the morning, running until around 1:32. We need lots of proctors. We have 1,400 hits coming to campus, so if you would like to participate, sign up at the front.
It's like maybe like
Okay, I need you to be quiet. Okay. Okay. So, just going to talk for about 15-20 minutes about magnetic dipoles and dipole moments. Quick refresh on where we kind of closed out on Tuesday. And now I'm going to turn our attention for maybe 10 minutes or so to a very, very simplified picture of an atom, a sort of classical picture of an atom, and see how that might relate to our simple ideas about magnetic dipoles and magnetic dipole moments. It's a very simple, idealized model. I'll mention briefly some of the actual real complexities that we have to consider, which have to do with quantum mechanics when we think about this stuff. And sadly, very briefly, we'll just allude to some very interesting sets of phenomena associated with atoms as magnetic dipoles in condensed materials, and the rich variety of materials that can arise when we look at this. And that gives rise to a few of the fun demonstrations up front and also on video. And then we're going to turn our attention for the rest of today and into Tuesday next week into the phenomenon of induction. Just an introductory comment about that, and then I'm going to jump right back into dipoles. If you think about what we've covered over the past 6 to 8 weeks, we started out with charges at rest, electrostatics. More recently, we've started looking at charges in motion, but generally speaking in motion at constant velocity, so they're not accelerating. And we've learned that that's really the source of magnetic phenomena. So starting in the middle of the way through today's class, we're going to look at cases where there's actually time-dependent phenomena. So something that changes with time. So we've gone from static to motion, but at constant velocity, now to accelerating charges. And it turns out this is where the sort of interplay of electricity and magnetism starts to become much more apparent and much more interesting. So that's our direction we're heading. In the remaining 2 weeks of class, we're going to be looking in more detail at how these two things interact with each other when, roughly speaking, there's some kind of acceleration in the system. So that's the roadmap. Okay, so let me take you back to Tuesday's class. We didn't do this in detail in class, but I talked you through how we would do it and then asked you to read my notes or the textbook. And it had to do with the phenomenon of, let's say, a single current carrying loop in yellow on the chalkboard, currents going around in the sense that we see there. What you had sort of derived for me was qualitatively that we expect to see a magnetic field pattern that looks like this. And somewhat quantitatively, we derived this result for the magnetic field at any point along the central axis that goes through the center of this current carrying loop. So what do we mean when we kind of think of this as maybe being a little bit like a magnetic dipole? Well, maybe I'll add some color onto this. The pattern of magnetic field lines that you see associated with this, and let me just remind you that the direction of those field lines we can get from the right-hand rule. Curled finger right-hand rule. I take my curled right-hand fingers, kind of have them trace the direction of the current around that loop, and my thumb gives me the direction of the magnetic field in the center of the beam. You can also do it in a slightly more elaborate way, which is what you guys did in class on Tuesday, which is look at each current carrying element here and do this as the way you have the field lines locally wrapping around that current carrying element. You superpose them all and you get this sort of pattern. Okay? So, in a sense, this of course looks not hugely dissimilar from the pattern of field lines that we would expect if we had a bar magnet. So in that sense, it looks rather similar in terms of the magnetic field lines that it produces. And so this already gives us a sense of some very close relationship between permanent magnets manifest in the form of bar magnets here versus electromagnets, which are cases where maybe we're specifically turning on macroscopic currents going around that loop, and we see that we're getting the same magnetic field effect in both cases. So, let me just say a couple of comments about the magnetic dipole moment. So, we can define the magnetic dipole moment mu as, let me just keep this as a scalar for the moment. Let's define it as, in this case, it's the current flowing around here times the cross-sectional area of that circular loop. We use the same notation here as we big R squared in this case. More generically, if we don't have a circular loop, it's just going to be the current multiplied by the area of the loop. Okay? So we're going to define the magnetic dipole moment now as the product of the current and the cross-sectional area. And again, it's always going to be defined in sense by the right-hand rule. So if I were to draw now a magnetic dipole moment vector on here, in blue, I would draw it something like this. Okay? So you've heard me at various points bemoan the unfortunate conventions that run through some of physics, because we run out of new distinct symbols to use for certain quantities. But let me just illustrate this a little bit in this case here. For example, if I look at this for a distance away that's much larger than the radius of this current carrying loop here, this expression becomes the following. And this is just for one particular instance of this. So it looks something like this. This is just taking this and the limit that x is way bigger than r, so I would get this as an approximate result of the magnetic field a long distance away along that perpendicular axis. And so I can also write this as mu 0 over 2 pi I r squared over x cubed. And now, making use of this definition of the magnetic dipole moment mu, this is where the horrors of duplications of symbols kicks in, I can now write the expression for the magnetic field a long distance away as this. What do I mean by the horrors of duplicate use of symbols? So now we've got mu 0 as the permeability of vacuum, and we have mu right next to it as something which is fairly distinct, namely the magnetic dipole moment associated with that loop cascade.
What if we put like a diamagnetic index?
Okay, so we're not going to talk at all, except in a qualitative manner in 10 minutes or so, about magnetism in materials, sadly. But yes, there's that complication as well. Okay? So there's a reason, aside from just what we can fit in this course, that I'm not doing that. All right? Okay, so, fine. And I think, as we talked about a little bit in the past, we can treat this when it's in an environment of an external magnetic field. We care about its orientation, forces that are exerted on it, specifically the torques that are exerted on it, and the potential energy that's associated with it. You'll remember we did a compare and contrast exercise with that a couple of sessions ago. So all of this is basically just a reminder of what we know from macroscopic current carrying loops. Now I want to take these ideas and just look at a very simplified model of an atom and see how much of this carries over and tells us something useful. So, magnetic dipole moment. For very idealized atoms. So, in what sense might the picture on the left-hand chalkboard be relevant to the simplified picture of an atom? Well, probably fairly obvious, right? let's take a simple single electron atom. Maybe it's a hydrogen atom. As you know, we have a positive nucleus at the center of our classical picture of, let's say, a hydrogen atom. And what we have, again, in the classical picture is we have a single electron circulating, maybe in this direction. So, okay. So, here's our positive nucleus circulating the electron. Just a footnote here, this is a negatively charged particle, but as you know, our convention in physics is to have the current go in the opposite direction. Okay? So let's see. Let's say that this has a radius little r, and that this thing is moving with a constant speed v around this circle. And we're going to assume, not about approximation in general, that the nucleus here is stationary. Okay? So why is that? Maybe possibly slightly something controversial. Of course, this thing has a mass, this thing has a mass, two objects rotating around each other. In fact, if you look at classical mechanics in a little bit of detail, you'll see that both of them have to be rotating around each other. But if this is way more massive than this one, we can treat this one as effectively at rest and just have this one orbiting around it. Okay. So there's our model. So what do we know about this? First off, we can say something about the period of rotation of our single electron orbiting around in uniform circular motion. So the circumference over the speed, 2 pi r over v. The current, in terms of charge and the period, so think of this as just being the charge on the electron. It's moving around one orbit in the period that we just determined. So it's this over this. And so this then is E times V over 2 pi r. Okay? So this, in a sense, is the magnitude of the current. Keep in mind that the current, as we always define it, is in the opposite direction of the electron motion itself. All right, so now we're going to take this and come back to our definition of the magnetic dipole moment. And of course, the picture that I've drawn here basically looks like this, except the current direction is in the opposite sense, and we're talking about vastly different scales. And we'll talk about that in just a moment. The magnetic dipole moment associated now with this orbiting electron. I'm going to put a subscript ORB down here to denote an orbiting electron. It's just the magnitude of the current times the cross-sectional area of the loop. We just determined what the current is. So I'm going to plug that in. The area of this, assuming it's circular, is just pi r squared. And it tells us that in terms of magnitude, we can approximate the magnetic dipole moment of this orbiting electron as EVR over 2. Okay? So, again, the right-hand rule determines the direction of the field in this time, in this case, as it does in that case. Well, let me just make sure you guys are awake. What direction is the magnetic field in this case? Okay, I see lots of people pointing down. Excellent, okay? Because it's negative charge going that way, so it's positive charge going in the opposite sense. All right, so just to give you an idea of the sort of scale here. So charge on an electron, 1.6 times 10 to the negative 19 coulombs. Speed, not necessarily something you would have an easy ballpark guess for. But let me see if you have a good sense of the typical radius of orbit for an electron in a simple atom like this, a hydrogen atom. What sort of scale are we talking here now? Let's go to Michael.
10 to the negative 27 meters.
Careful.
Wait, no, that's I'm thinking mass.
Go ahead.
It's -5.
Okay. Got a very enthusiastic respondent, but I'm going to have you on tenterhooks a little while longer. Yes. All right. So, roughly of order 10 to the minus 9, 10 to the minus 10 meters. Okay. So, all of this to say that the typical orders of magnitude for these magnetic dipole moments associated with electrons orbiting atomic nuclei is about 10 to the minus 24. 10 to the minus 23 ampere meters squared. Okay, so obviously very small compared to anything macroscopic, but it's a real effect and it's there. Okay, I'm not going to say anything about a piece of technical jargon, it's not needed. Let me just point out one thing that you know, which is just to have you think about the relative orientation of the angular momentum vector associated with this orbiting electron and its magnetic dipole moment vector. Okay, you just told me what direction the magnetic dipole moment vector is pointing in this case, namely down. But in terms of the angular momentum vector of that orbiting electron, which direction is that? Back to first semester, again, right-hand rule, we're just looking at this in terms of mechanics and angular momentum vectors. What direction is the L vector of this orbiting electron? Thank you, Noah. It's upwards. Okay, so let me just, this is all a lot of FYI stuff, and again, sadly we have not enough time to go into much of this. But the angular momentum vector in this case is upwards, and the magnetic dipole moment is downwards. Okay? All right, so that's our very simple classical picture of a single electron atom. In reality, life's way more interesting. And the interest comes when we, as we always need to do with things at a small scale, need to transition from classical mechanics to a quantum mechanical treatment. So this tells us, in fact, without any other knowledge, that our magnetic dipole moment could take any possible value at all. It's a continuous quantity, if you will. This is quantized, which is to say it has a particular phase value, but these things, in a sense, as far as we know, are variable. They're continuously variable. So the magnetic dipole moment itself, according to classical physics, is a continuously variable quantity. But as with most things in quantum mechanics, when you look at the world at small scale, where, and some of you were asking me about this just as class started, things we usually think of as particles, we are better off treating as wave-like behaviors. And when you do this, you find out that many intrinsic quantities of particles at small scales are quantized, which is to say they can come with only certain discretely spaced values of most physical quantities. And so just as an FYI, so if we add quantum mechanics, it turns out that this orbital magnetic dipole moment associated with electrons can be characterized in terms of rather different variables, namely, most importantly, in terms of this. Okay, so we're not really going to talk about this at all in this course. Sadly, those of you going on to the third semester will do a lot to do with this. This is Planck's constant, and it is the sort of defining scale that tells us when we have to transition from classical to quantum perspective or treatment of things. And what this most crucially is telling us is, first off, well, this is a constant, it's a certain number. I'm not even going to tell you the value. It's very small. It's probably all you need to know. Here we have two physically defined parameters for our orbiting electron, namely the charge it carries and its mass. So these are physically presented quantities for us. And then the other absolutely critical thing, which is a feature always of quantum phenomena, is this is an integer. So apparently, according to quantum mechanics, our orbital magnetic dipole moment for our electrons orbiting an atom can only come in integer multiples of all of this stuff. Okay? So an interesting piece of information. We're not going to make any further use of it, but just something that's kind of nice to know about. Let me just say one second footnote comment, and then we'll just turn a little bit to the impact this has on bulk materials. So I've described a single orbiting electron moving around in a typical radius, 10 to the minus 9, 10 to the minus 10 meters. It has a magnetic dipole moment associated with it. Turns out, and again, something that's absolutely intrinsic to quantum mechanics, that essentially all fundamental particles, or all particles that make up matter, have intrinsic within themselves a sort of characteristic that in some respects they seem to be spinning. Okay? So this electron, which we kind of treated up until this point as being a point-like particle, turns out we have to treat it as though itself it is spinning. Okay? Now the electron carries charge, and again this is a sort of wildly incorrect classical picture. It carries charge, imagine it as a kind of spinning top. If it carries charge and it's spinning, if it has any finite size, then there's some part of that charge which is a finite distance away from the axis of rotation. So now on a vastly different scale, we have charge that's intrinsic to the electron itself, spinning about its internal axis of rotation. So again, a wildly incorrect classical image to have you think about, but what it also means is that particles themselves, without worrying about them orbiting about other particles, the particles themselves have intrinsic magnetic dipole moments, okay? And these are often called spin magnetic dipole moments. So in contrast to an orbital magnetic dipole moment associated with the motion of electrons around a parent nucleus, this is a spin magnetic dipole moment that's associated with the apparent spinning of these particles themselves around some kind of internal axis. So again, just as an FYI, for any of you who go on to do more physics, anything to do with materials, atomic, molecular physics, all of this is obviously super important, but sadly not the thing that we have time to cover in this course. All right, so let me just do a few minutes of random things about what happens macroscopically when we have a lot of these atoms together in the system. And then I'll show you a few quick demonstrations. So, we've seen how at the atomic scale magnetic behavior might arise. For our purposes, it's really just the picture behind me, orbiting electrons, producing magnetic dipole moments. In materials absent any other effects, you might imagine if you put a bunch of these atoms close together in some condensed matter system, you might have those orientations of the orbital angular momentum just kind of being pointing in random directions. Remember, the whole point of this is that we want to have some explanation for macroscopic magnetic phenomena. So, again, absent other knowledge, that might tell us why most materials are non-magnetic, because the atoms that make it up have these orientated magnetic dipole moments just in random directions. So they all cancel each other out. And that's kind of true. But quantum mechanics tells us a bunch of other things. Firstly, it turns out that there's a very famous and powerful principle in quantum mechanics that no two electrons in some system, which is always a little bit tricky to define, but no two electrons in a single system should have the exact same characteristics as each other. This is the so-called Pauli exclusion principle, and it turns out that the world that we live in is governed by this principle that multiple electrons in a given system have to have something that distinguishes them from all of their neighbors. They have to have, in the lingo of quantum mechanics, at least one quantum number that describes their state that is different from all of their neighbors. And one way this manifests itself in multi-electron atoms, remember this was just basically a simple hydrogen atom with one electron, but if I add a second electron and make this a helium atom, now I have, let's say, 2 protons, 2 neutrons in the nucleus, and I have 2 orbiting electrons. So quantum mechanics tells us that the preferred way to have those 2 orbiting electrons move is such that they actually, in a very incorrect classical picture, are orbiting in opposite directions. So their orbital angular momenta prefer to anti-align, okay? And it turns out as you add successively more electrons to more complex atoms, we have very interesting rules which basically allow us to build up the periodic table of how these electrons should be added, okay? So, if for some reason we have a condensed material where we have somehow aligned the magnetic dipole moments of nearby atoms, that's not a preferred configuration based on the Pauli exclusion principle. And the sort of effect of this is that those atoms, in a sense, kind of like to push each other apart a little bit. They don't like to have their orbital angular momenta aligned, so they, in a sense, kind of exert a repulsive force on each other. A lot of interesting stuff going on here, but I want to try and quickly motivate how this might inform behaviors of certain types of materials in the bulk. So I'm going to show you just quickly 4 demonstrations, I think. First off, ferromagnetism. These are materials that seem to behave like permanent magnets, iron, steel, you know them well. And what's happening in ferromagnets is indeed that there's sort of locked in some macroscopic alignment of the orbital angular momenta of nearby atoms. In practice, this alignment is not perfect, and interestingly enough, in many materials, in different parts of the material, there are regions where the alignment may kind of be in different directions. For those of you who go on into more of this, you may hear the phrase magnetic domains. These are quasi-macroscopic regions in the material where the spins are all aligned in one direction, but then there's a sort of break, and then they're all aligned in another direction. These are so-called magnetic domains. So you can imagine this, you've seen this demonstration a little bit before, but you can imagine this now as being not exactly random at this point, partly because of the way this thing is set up, but also partly because it had a dipole magnet sitting on it a moment ago. You can imagine this as being a piece of unmagnetized macroscopic material where each of those little arrows corresponds to the alignment of the angular, the magnetic dipole on each atom, let's say. So random alignments. And then we can perhaps take materials, and these are the ones that we would describe as ferromagnetic, and somehow get macroscopic regions where they all align in the same direction. So I'm going to show you that with this. So this right now is a loop of steel, and it's been split in 2, and then the 2 pieces are kind of strung together as you see it here. So right now, separated, I bring them together, not much happens, I let go, they fall apart again. But, so this is unmagnetized for the most part. What you see is that it's also connected to this current source, and I'm just going to show you what happens if I energize the current source. Before I turn it on, let me just show you what you're looking at. So these things are connected to this. You can't see it, but it's a loop of current carrying wire. Many, many turns, and as you know, many, many turns amplifies effects. So if I drive current through this loop, what do you expect it's going to do in terms of the nearby magnetic field through its center, that sort of central part of the loop? It's going to produce a magnetic field, right? And you know it's going to be somewhat like this, so it's going to be kind of along the direction of the steel. So I'm going to do this, but actually do that. I don't really have time to talk about the overall effect here, but take this thing and kind of try and transpose it onto something which has a sort of circular geometry like this. It turns out that the steel also has a little bit the effect of, in a sense, focusing the magnetic field lines. So as you know, these things wrap around, but if I have a sort of core of steel here, it will tend to channel those magnetic field lines through the steel as opposed to the surrounding empty space. So I'm going to turn this on. So I just energized this thing. And of course now it sticks together. Okay? So the reason it sticks together is I've got a magnetic field set up in this region. The field lines again are sort of concentrated around the entire loop. And it's tending to line up most of the, it's not a very good exact geometrical analogy here, it's tending to line up, whoa. First time I finally made something smoke. Good. Oh, it smells good. This happened before I had set the scene for it, but now I just turn the power off. And you see they're still stuck together. So I have, in fact, by driving current around this thing, I've set up a preferred orientation of all the magnetic dipole moments in the steel, and it persists once I remove the current, once I remove the magnetic field that I've set up by turning this thing on. So this has no longer got any current flowing through it, and yet the thing is magnetized. Okay? So this is ferromagnetic behavior, and this is one way of creating things like bar magnets. Obviously the geometry is different, but that's one way to do it. Okay? Ferromagnetic behavior, lots to talk about there, but sadly no time. All right, a couple of other things to say. There are more subtle types of things that could happen, depending on the structure of the atoms or molecules that make up the material. And all I'm going to say here is a little bit related to a comment that Keithan made about putting materials that are so-called paramagnetic or diamagnetic in a magnetic